The working principle of a MOSFET. First, let's look at the flow of current and electrons in a basic circuit. As shown, the current flows from the positive terminal to the negative terminal of the battery. And the electric field also points from the battery's positive to negative outside. Electrons flow in the opposite direction from the negative terminal to the positive terminal. A MOSFET is made of semiconductor material such as silicon, whose conductivity lies between a conductor and an insulator. To improve conductivity, impurities are introduced into pure silicon, which is called doping. The dopants can be of two types. One is pentavalent elements like phosphorus, producing an N-type semiconductor, where the main carriers are free electrons in the conduction band. If trivalent elements such as boron are doped, a p-type semiconductor is formed where the main carriers are holes in the valence band. When they are connected at their junction, the p-n junction, free electrons from the n-type region fill the holes in the p-type region. As a result, charges near the junction are depleted, forming what is called the depletion region. If the p-type is connected to the battery's positive and n-type to the negative, the depletion region narrows, allowing current to flow. This is forward bias. Conversely, reversing the battery terminals widens the depletion region, stopping current flow. This is reverse bias. That's the necessary background. Now, let's look at MOSFETs, which have two types, enhancement and depletion. Each can be further divided into N-channel and P-channel, as mentioned yesterday in inverters. Today, we use an N-channel enhancement MOSFET as an example. Its structure: yellow is N-type, blue is P-type. The lower terminal is connected to the substrate, thus called the substrate terminal. The two terminals in the N-type region are called source and drain. Between these terminals is a thin insulator or dielectric, above which another terminal is connected, the gate. These are the four terminals of a MOSFET. Due to its symmetry, the source and drain can be interchanged. The source and substrate are internally connected, effectively making it a three-terminal device. Since they share the same potential, no current flows from substrate to source. Now we want conventional current to flow from drain to source. To achieve this, we can apply a voltage between drain and source. Since it is between drain and source, this voltage is called VDS. We can also express the relationship between drain current and VDS using a curve. Specifically, the positive terminal raises the drain potential. This enlarges the depletion region between drain and substrate. According to reverse bias, no current flows from drain to source, putting the MOSFET in cutoff, also called the cutoff region. How to make current flow from drain to source? By creating a new channel between them. Specifically, apply a voltage between gate and source, positive to gate, negative to source. Since it is between gate and source, this voltage is called VGs. Looking at current, the substrate is p-type blue, with holes as main carriers, but few free electrons still exist. The gate voltage creates a downward electric field, causing substrate electrons to move opposite the field toward the gate. The thin insulator prevents electrons from reaching the gate, so they accumulate beneath it. Like a capacitor which stores charge on two plates with a dielectric in between, the MOSFET's insulator increases nearby charge. Similarly, the MOSFET insulator blocks electrons from the gate while increasing nearby charges, attracting more free electrons. Increasing VGs gathers more electrons near the gate, filling holes in the substrate. The holes are repelled from the gate, moving deeper into the substrate. Now the region near the gate has mostly electrons, effectively forming N-type material. Thus, a channel forms between source and drain, allowing electrons to flow from source to drain. The channel thickness can be controlled by VGs. It's proportional to VGs. The minimum voltage to form a channel is the threshold voltage. Then electrons flow from source to drain, so conventional current flows from drain to source. Source supplies electrons to the channel, drain collects them. Since current flows from drain to source, it's called drain current. At this stage, ID is linearly proportional to VDS, showing resistive behavior. The MOSFET is in the ohmic region. Ohm's law applies. As voltage increases, current increases, but the depletion region at the drain expands with reverse bias. The channel near the drain narrows due to the positive drain voltage attracting nearby electrons, reducing current. As voltage increases, the channel shrinks. When width reaches a critical point, pinch-off occurs. In reality, the channel is not fully closed. Many electrons remain, so current does not stop but saturates. This is saturation current, and the corresponding voltage is saturation voltage. Increasing voltage further increases reverse bias, shrinking the channel more, but current stays constant in saturation region. If we want more current, we can increase VGs, which widens the channel controlled by the gate. Increasing voltage further increases current. When pinch-off occurs again, the MOSFET enters the next saturation region.